All right, in section 9.2, we're going to continue our study of trigonometric identities. There are actually a lot of trigonometric identities. I did mention in the last section that technically there's an infinite number of trigonometric identities, but the ones we were looking at last section are all ones that can be proven just by applying algebra rules and the basic trig identities that we've already established, like the ones that I listed in that first video. So, it turns out there are lots of other trigonometric identities, some of which involve things like adding or subtracting angles together. So in this section, 9.2, we're going to learn what's called the sum and difference identities, and they are these. So the idea of these identities is to figure out the cosine and sine of either a sum or a difference of two angles, and get that in terms of the cosine and sine of the individual angles themselves. So the key thing is here, if we know cosine and sine for alpha and for beta, then these formulas give us ways of calculating the cosine and the sine of alpha plus beta or alpha minus beta. Okay, so by the way here, I've color-coded the plus. If this is an alpha plus beta, then this is a minus in the formula. And if this is an alpha minus beta, then this is a plus in the formula. And then this plus or minus corresponds to a plus or minus over here. Okay, so plus goes with plus, minus goes with minus for sine, whereas with cosine, the plus goes with minus and the minus goes with plus. So please pay attention to that color coding in the corresponding operations. This is also written upside down to indicate that it's the opposite sign to whatever that was. Okay. So I'm going to start by showing you a proof of one of these identities. These cannot be proven like we were proving things in the last section. We need to do a little bit more work to prove one of these. So I'm going to put that aside for the moment. Here I have two circles drawn. Now I've gone all out with actually tracing circles and using a ruler and all kinds of stuff for this one. All right, so usually I just draw a rough circle and go with it, but this time we're gonna do things properly. So we have two circles, and then we have two angles, with several different angles at play here. We've got alpha and beta. Now I just picked some random alpha and beta, but the formulas technically are valid for any alpha and any beta, any angles you want, whether they be positive or negative, no matter how big or small. So here's an alpha and a beta. Now on the left, in the left diagram here, I've drawn alpha plus beta. Okay, so alpha and then beta is measured from alpha continuing on. So if you add angles, you can measure and then keep measuring. So that's what we see here, alpha and then beta. So that all the way over here would be alpha plus beta. Okay, this point is 1, 0, and then this coordinates of this point up here would be the cosine and sine of alpha plus beta, which is the full angle that takes us from the positive x-axis over to that terminal side. Now on the right-hand diagram, we've got alpha graphed individually. So here's alpha by itself, and then here's beta graphed individually. Here's beta by itself. So these two terminal points have cosine and sine for alpha and then beta, respectively. Okay. The other thing that's graphed over here is the negative alpha. So I've taken one of these two angles and I have reflected it over the x-axis here. And this dotted line here is meant to indicate a vertical line. So that means the cosine values are actually going to be the same. The x-coordinates will actually be the same. And the sine values will actually be opposites of one another. Now that is kind of reflected in the odd and even identities for cosine and sine. So this is cosine and sine of negative alpha, which is the angle, but then odd and even identities would tell us this is actually cosine of positive alpha, and then negative sine of positive alpha. Okay, and that's the same thing I was kind of justifying with the geometry there as well, with that dotted line. Okay, so now we get to do something where we're going to draw two lines and claim that their distances, or the lengths of those two line segments, are going to be equal to each other. I'm going to get a red pen here. All right, I'm going to draw a line segment connecting these 2 points, like so. And I'm going to draw a line segment connecting these 2 points, like so. Now I claim those line segments are the same length. Let's call them distance 1 and distance 2. Now the reason those are the same length is because these are both unit circles, all right? Both of these are unit circles. And the angle in the middle, like the whole angle that this line is capturing here. That full angle is alpha plus beta. And this full angle here, since it was beta up and alpha down, that's also alpha plus beta. So they both have an interior angle, which is the same. They're just one as sort of a rotated version of the other. But those distances should equal each other. So the first thing I'm going to write down here is d1 equals d2. Now the fact that d1 equals d2 means that I should be able to use the distance formula. Remember the distance formula, square root of difference in x's squared plus difference in y's squared, y2 minus y1 squared. That distance formula right there can be used to calculate the length d1 and the length d2 in terms of the coordinates of the points, which are going to be cosines and sines of various angles. Okay, so now we're going to start doing, now I'm going to show you a rather long and messy set of steps where we're going to do a bunch of algebra and a bunch of simplifying. So this is going to get really big and messy, and then it's going to simplify and boil down to the formula that we want. So the d1, left side here, is going to be a big square root. And what's underneath that square root is a difference in x's squared plus a difference in y's squared. So the difference in x's between these 2 points, I'm going to do this point minus this point. So it's going to be cosine of alpha plus beta minus 1, and then that's squared. Then we're going to add the difference in y's squared, which is going to be sine of alpha plus beta minus 0, and then that squared. So that's all of that is underneath our square root. That's d1. d2, similarly, we can take a big square root. For d2 over here, difference in x's, we're going to take the difference in these x coordinates, and I'm going to use this version and this one here. I'm going to use this version where the negatives have been dealt with via the even and odd identities. So here I'm going to get cosine of beta minus cosine of alpha squared plus, and then we'll do the sines, sine of beta minus a negative sine of alpha. So I'm actually going to turn that into a plus sine of alpha, and then that is squared. Yeah, no matter how long I make my square root bar, I never ever make it long enough. I always have to extend it, because it always takes more space than I expected. So there we go. Now I'm going to go through and do a bit of color coding. Let's grab this segment here, and we're going to simplify that. Oh, I forgot. Before I simplify that, both sides of this equation are currently a square root. The first thing we should do is square both sides, which is going to cancel out that square root. Okay, that's gone. Now we don't need to worry about any negatives and positives, because what's underneath these is guaranteed to be positive anyway, because of all the squaring that we're doing. Okay, now imagine that the square roots are gone, and now we're going to simplify each of these bits, and we're going to expand everything and do a bunch of work. So over here, we're squaring. I'm going to keep using the formula, the formula that's like a plus b squared is a squared plus 2ab plus b squared. I'm going to use that formula a bunch of times. So here we're going to get cosine squared, alpha plus beta, minus, because this is subtraction here, minus 2 times cosine of alpha plus beta, and then plus 1, which is negative 1 squared. Then on this side, the minus 0 doesn't matter, so this is just plus sine squared of alpha plus beta. So far, this portion here came from the purple underlined bit, and then this portion here simplifies to just that one term. That would be the green underlined bit. Next, on the right-hand side, let's use red next. The cosine beta minus cosine alpha squared, that's going to simplify to, or not simplify, that's going to expand to give me cosine squared beta minus 2 cosine of alpha times cosine of beta, and then plus cosine squared alpha. So that whole segment comes from the red underlined bit. And then the last color, what's my last color? Blue. I knew I had 4 colors lying around here. So that blue bit is the last part to do, so I'm going to write plus. I'm going to have to go on down to a second line here because I'm running out of space. Plus, we're going to get sine squared of beta plus 2 sine alpha sine beta, and then plus sine squared alpha. That whole segment there is blue. Okay, now I'm going to get out the highlighter. Man, this requires so many different colors. Where's my highlighter? Hang on a moment. There we go. So now, a lot of pieces of this are going to combine together to give me 1. So check out over here. I've got cosine squared alpha plus beta. Okay, cosine squared alpha plus beta. If I can find a sine squared of alpha plus beta, because alpha plus beta is the same, because the angle input is the same, cosine squared plus sine squared should equal 1. We have a plus sine squared right there. So that pair together, those two are gonna match up and give me 1 via the Pythagorean identity. Cosine squared plus sine squared equals 1. Now on the right-hand side, I do have cosine squared beta. So if we can find a plus sine squared beta, which we can right here, plus sine squared beta, those two are going to match up and give me 1. And then over here I have a positive cosine squared alpha, and here's a plus sine squared alpha. So those two are going to match up and give me 1. So I have these pairs which by Pythagorean identity are going to end up equaling 1. Okay, so now using that, we're going to have 1 from this pair plus the one that's already there. Okay, plus the one that's already there, so that's 2. And then minus this other term, 2 times cosine of alpha plus beta. Equals, over on the right, I have a 1 from this pair plus a 1 from this pair, so that's 2. And then I've got these other two terms, so like minus 2 times cosine alpha, cosine beta, and then plus 2 times sine alpha, sine beta. All right, we're almost there, because now we can subtract 2, cancel those out. So now from this term on the left side, all we need to do is, we got that term on the left, and then we have each of these terms. All we need to do is divide by -2, and divide everything by -2. Divide by -2, divide by -2. -2's cancel out, and what we get, I ran out of space at the end, but what we get here, I'll try to squeeze it in. We've got cosine of alpha plus beta on the left side, and on the right side, canceling -2's, we've got cosine of alpha times cosine of beta. And then this was plus, you see, but we're dividing by -2, so the 2's cancel, but then negative sticks around to give us minus sine alpha times sine of beta. And that right there, put a big star by that, that is one, let me push it up here, that is one of the 4 identities that we're looking at here. So for the cosine alpha plus beta, that's one of them. So this, so that's what we have, and that's what we just proved. So this proof establishes only one of the 4, but there's sort of similar proofs you can do with the same kind of reasoning, just set it up with slightly different combinations of angles, and you can get all of these identities proved in a similar way. Okay, so you never have to reproduce that proof, but I wanted to show it to you. Now in the next video, we're going to go back to this page, and we're going to I'm going to show you how to use these formulas to do useful things. Oops.